Okay, now we are on the topic of foam and emulsion. In Modo, I think we have been doing some discussion, and some of you have uploaded good videos on related to emulsion and foam, and I have also uploaded some videos to share with all the students. Okay, Asmilia just joined. Welcome, Asmilia. All right, we will start by discussing about droplet size distribution. If you remember, in the last lecture, we discussed about the three types of emulsion having different size distribution, and I asked you a question: which emulsion is the most stable? Okay, basically, if we have used the proper equipment such as the high-speed homogenizer or high-speed mixer to disperse the liquid to prepare the emulsion, we should get a good emulsion with more or less a homogeneous distribution of the droplets, as you can see in the picture here. So you can see there's droplets distributed in the emulsion, but still you can see there are different sizes of droplets in this emulsion if we look under microscope. If we leave the emulsion over a period of time, then what we will see, if we look under the microscope, say after half an hour or after 1 hour, we can see now there are different sizes. We can see quite clearly there are different sizes of droplets in emulsion. So there's a big one, there's a small one, and so on. So this is actually what will happen when after we prepare the emulsion, and it depends on how fast the emulsion will change in the droplet size distribution depending on the stability of the emulsion. Okay, so later we will discuss about the emulsion stability, but we have to remember that emulsion is actually thermodynamically is an unstable system. They try to separate again into two layers, because that is in the most stable form when they are separated into two layers. But when we force them to separate into droplets like this, they tend to over time they tend to come together and merge and form a bigger droplets. So this is the reason why we have to find ways to stabilize the emulsion by adding emulsifiers and by using other factors such as increasing the viscosity of the continuous. Okay, remember this slide last week? Okay, we have three emulsion here: emulsion 1, emulsion 3, and emulsion 4. And I asked a question in the lecture: which emulsion do you think is the most stable? Okay, and I have introduced the term polydispersity to show the distribution of the droplets in emulsion, which can be described as monodisperse and polydisperse. Okay, now let me switch the screen. This is a question that we discussed last week based on the diagram. Okay, what I want to do now is to note down. Do you have a pen and a piece of paper? Let's do this exercise now. Okay, I want you to choose emulsion 1, emulsion 3, and emulsion 5. Which one is the most stable? So note down the code 9. Okay, you note down this code, then go to this web page. So note down, you open another window on your computer, type this address http://polev.com. So when you open this web page, you submit the code which is the answer for the question just now. Submit the code. Which one or which emulsion is the most stable? Do you get that? Do you get this instruction? We will go back to the diagram just now. Maybe you don't remember now which one is emulsion 1, which one is emulsion 3, and which one is emulsion 5. But please note down the answer and the code, and note down the address of the website. This is where you will submit the answer. You don't have to use the handphone, but you can submit the answer through the web page here. Okay. Already someone already sent the answer. If you have your notes there, you can refer to the diagram, so that I don't have to switch to the PowerPoint. So now we can start to see the answer coming on the screen. Okay, we have 2 students already submitted the answer. What about others? Okay, I will switch back to the PowerPoint. In case you don't have your notes there, we can refer to the diagram. At the same time, you can submit your answer online through the web page. Okay. Okay. Now this is the diagram. Emulsion 1, emulsion 3, and emulsion 5. The question is, which emulsion do you think is the most stable based on the droplet size distribution here? Okay. Okay. Now, while you are thinking the answer for this question, I have explained to you last week the term polydispersity, which describe how wide the distribution of the droplets in the emulsion. So for emulsion 3, for example, we can see that it has a very narrow distribution, which means that the variation of the droplets in the emulsion is quite small. Yeah, the difference between one droplet size to another droplet is not so large. So that's why we have a narrow size distribution. So for this type of distribution, for emulsion 3, we say that emulsion 3 has a monodisperse distribution, whereas emulsion 5 and emulsion 1, in comparison to emulsion 3, is more has a wider size distribution. So we can say they are more polydispersed. Okay. So we will come back to the poll just now and see whether you can answer correctly which emulsion has a highest stability. But one point that I want to stress here, what we see here on the screen, the size distribution that we see in the screen, is actually usually you can observe only for a freshly prepared emulsion. Okay, this is the ideal kind of droplet size distribution that you want to see in the emulsion. But when we leave the emulsion to, let's say we store the emulsion and leave it to stand on the table for 1 hour or for 2 hours, then after that we measure, using the instrument, we measure the size distribution again. And do you think you will see the same kind of shape or the same kind of distribution after 1 hour or after 2 hours? Okay, yes or no? Please answer yes or no. Or who say yes, you can raise your hand also. No. Sumaya says no. Kapu says no. Asmilia says no. Huikin says no. What about others? Angela? Okay, good. Daisy? Daisy, can you hear me? Okay, yes or no? The question is, after you leave the emulsion for 1 hour or even 2 hours, would you observe the same kind of distribution again? Okay, most of you. Alright, what about Yongsheng? I don't get your answer. Yes or no? Alright, good. Yes. Definitely you won't get the same type of distribution. Let's say we start with emulsion 5. So this is the freshly prepared emulsion, and the size distribution you can see ranging from there to around 1 micron. If we come back for say after 1 hour or 2 hours, most likely, especially if the emulsion is not very stable, most likely you will get another curve which is similar to emulsion 1. Okay, which means that it has shifted to higher diameter because maybe some of the droplets has combined or merged and coalesced to form a bigger droplets. So this is actually one way how we can monitor or measure the emulsion stability by using by looking at the droplet size distribution by using an instrument. So this is one important aspect actually on emulsion that you have to understand, which is the way how we can measure the emulsion stability. Then when we have this instrument and this diagram, we can do some experiment by using different type of emulsifiers, by using different type of stabilizers. Then we measure the size distribution again as a function of time. Then we can see, and the experiment will tell us which emulsifier and which stabilizer would be the best in order to give the kind of stability that we want for our emulsion. Okay, so I would like to switch back very quickly to the web page and see what we got. Okay, so 9 students has submitted their answer, and we have 100% students say yes. I mean, say emulsion 3 as the most stable. Okay, what about others? I don't know whether you have submitted or not. We have around, I don't know, about 9 students online here. Okay, that's okay. Okay, let's switch back to PowerPoint. Okay, emulsion 3 is this one. This is a kind of monodisperse emulsion where the size distribution is more or less uniform, and also we can see the mean size compared to emulsion 1 is smaller, but compared to emulsion 5 the size is slightly bigger in terms of the mean diameter. Okay, so between the emulsion 3 and emulsion 5, because although the mean average of emulsion 3, the mean average of the droplet is slightly bigger, but in terms of the size distribution they are more narrower. So most likely we, in this case we can get emulsion 3 would give us the most stable emulsion compared to emulsion 1 especially. Okay, and between emulsion 5 and emulsion 3, maybe emulsion 3 would have a slightly higher stability compared to emulsion 5. Okay, so that's how we interpret the graph. So now I have explained to you about volume fraction in the last week lecture. Maybe I will skip this part. Okay, now I would like to start with talking about the this one also actually I have covered. But the interesting thing about food colloids system is when we talk about food emulsion or food colloids, they are a very complex system. It's not just oil and water. It's not just fat and aqueous phase. But almost in all food, we have soluble solid, such as sugar or salt, flavor. We have foam. We have all sort of other things, colors and so on. So what we have in food is actually a complex emulsion, such as shown in this diagram. So for example, we have oil in water emulsion, but at the same time we have sugar dissolved in the aqueous solution. We can have foam. So this diagram is actually one food that probably can represent this kind of system. We can use as a good example is ice cream. Okay, so I've given you actually a reading assignment, or not reading assignment, but for you to practice. Sorry, for you to read more about ice cream as a complex emulsion and foam system. So now let's talk about surface and interfacial tension. How do we define surface tension and interfacial tension? So surface tension is the property of a liquid in contact with air, okay, that makes it behave as if it was covered with a thin membrane under tension. Okay, the term surface tension usually refers to interface between a liquid and air. For when we have a liquid and a liquid, then we use the term interfacial tension. So you have to differentiate between these two terms. But the phenomenon of surface tension can be seen every day in daily life around us. If you walk around in the morning, early morning, you can see the dew, is the embun, which has a spherical shape like this. And we can see, for example, on the surface of water, the insect can move and crawl or walk on the surface of the water freely. So this is actually a phenomenon of surface tension. What we see here is actually the interface between a liquid and the air. Okay. So if we look closely, the interface between air here and the liquid, let's say water. So we have the molecules inside the liquid, and each molecule will have attractive force among the molecules, with the molecules around the molecule itself. So suppose for this molecule we have the molecule on the top, on the left, right, behind, surrounding the molecule. So there will be a force of attraction in the form of hydrogen bond and other weaker bond. So they are always attracted to each other. But then the molecule on the surface only attracted to the molecules below it, but there is no molecules above it, which is on the air. So therefore, there is a tendency for the molecules to pull down the molecules on the surface, and therefore give a spherical shape, and because of the attractive force of the molecule inside the liquid, it gives a kind of a membrane or a layer which we describe as a surface tension. So this is a description of the diagram just now. The molecule inside the liquid interact equally with other molecules from all sides, whereas the molecule at the surface is affected only by the molecule below it. The molecules exposed to air behave differently and try to contract to the smallest possible area, and hence give a spherical shape. So we define surface tension. Okay, the unit is Newton per meter. We define surface tension as the force acting over the surface of the liquid per unit length of the surface perpendicular to the force. Okay, so it's defined as force, Newton, acting over the surface per unit length per meter. So that's how we define surface tension. Whereas another way of defining surface tension is as the amount of energy required to increase the surface area between a liquid and a gas, for example between air and water, by an amount of delta A. So we define as energy required, the amount of energy required to expand or to increase the surface area by the amount of delta A. I think this is quite easy to understand, because remember, in order to disperse one phase into another phase, so for example emulsion, we disperse a liquid into another liquid, or in foam we want to disperse air into a liquid. Okay, I just want to check. I have 3 cross mark here. I don't know what it means. Kafui, can you hear me, or you lost the audio? Kafui, Sukfwan, and Elizabeth. Can you hear me, or do you have any problem? Okay, Angela, Elizabeth, okay. What about Kafui? Okay, no problem, yeah? Alright, okay. Okay, let me just make a quick check, because I'm not sure, because I'm just talking here. Please say yes again if you can hear me so far clearly. Please say yes or no if you don't hear me. Alright, Min Ing, sorry. Min Ing, Daisy, Elizabeth, Sukfan, okay. Weishan, Huikin, Yong Sheng. Please say yes or no, Yong Sheng, whether you can hear me. Okay, good. Asmilia, can you hear me clearly? Please say yes or no. Okay, good. Fatina, alright, good. So I can continue. Okay, why do we define surface tension as the amount of energy required to increase the surface area? Because we need energy to break or to disperse one phase into another phase. How do we supply this energy? Okay, please type in the chat box. How do we supply the energy to disperse one phase into another phase? Can you all please type in the chat box? The question is, how do we apply energy, and what form of energy? Is it heat energy? Okay, let's have some interaction here. When we say energy, first, what form of energy we can use or we can apply, and how do we apply that form of energy? You can type in the chat box to give your answer. I don't get any answer. question is, what form of energy do you apply, and how do you apply the energy? If you don't know, just maybe we say don't know. At least I know that you can hear me. Okay, as Milia said, is that natural energy? Not really, not exactly. What about others? So the question is, what form of energy to apply, and how do we apply the energy? Okay, Kapu, you don't know the answer. Lishan? Alright, never mind. Okay, what the form of energy that we can apply when we want to form an emulsion is actually called mechanical energy. And how do we apply this mechanical energy? By mixing, by using high-speed mixer, okay, or by using homogenizer, okay, right? So by using this mechanical energy, we can disperse one liquid into another liquid to form an emulsion, or we can disperse air into a liquid to form a foam. Okay, so that's why we define surface tension also as a form of, as the amount of energy required to increase the surface area by the amount of delta A. Okay, what about interfacial tension? Interfacial tension is defined as the amount of energy required to increase the interfacial area between two immiscible liquids. So it is a liquid and liquid. For example, in this picture, we are dispersing oil into another oil. So the droplets that will be formed, the interface between the oil droplets and the continuous phase is called interfacial tension. Okay, so that's the difference between these two terms, the surface tension and interfacial tension. Okay, why is the interfacial area? Why is it important to get a large interfacial area to form stable emulsion? So one very important quality of the colloids is the large interfacial area between the dispersed and the continuous phase. This can be shown very clearly in this example, simple example, to illustrate the importance of having a large interfacial area to get a good stable emulsion. So in this example, we have emulsion, oil dispersed into aqueous phase. So in this case, we have 20 cubic centimeter of oil, each one having 1 cm radius droplets. So we can calculate by using a formula to calculate the volume of each droplet. So we get 5.5 cubic cm, and each droplet has 12.5 cm square. So in 20 cm cubic of oil, with this size of droplet, we probably get around 3.6 droplet and the total area of 45.5 cm square. Okay, but then if we use, say, high-speed mixer or high-speed homogenizer, and we can break up the droplets even into even a smaller size. So now each one would have a mean diameter of 0.1 cm and a volume of 0.004 cm cubic and a surface area of 0.125. But since now we have a large number of small droplets, say about, we can have around 5,000 droplets, and the interfacial area increased significantly from about 50 to 625 cm square. So this simple example illustrates how an efficient mixing system or dispersion system can actually increase the interfacial area significantly, and therefore increase the stability of the emulsion also significantly. Okay, so now now the time is around about 12 minutes to 11. Okay, let's see how many slides we can do before we end this lecture. Okay, now let's talk about the food emulsion itself. Remember, one of the important characteristic of food emulsion is that it's not a simple emulsion. It's not just oil and water, but we have other things. For example, in mayonnaise, we can have other ingredients. We can add acid. We can add vinegar. We can add flavor, and so on. Okay, so it's a complex system. So food emulsion usually consists of two immiscible liquids, oil and water, with one of the liquids dispersed as small spherical droplets in the other. So we get emulsion. So in general, the droplet size range from 0.1 to 100 micron. But in order to get a good stable emulsion, we'll try to get to as close to 0.1 or a very, very fine droplet distribution and as uniform size as possible. So basically there are two types of simple emulsion: water in oil, or W/O. So for example, margarine, butter, and spread. So this is an example of a small water droplet is dispersed into the continuous oil phase. And we have also oil in water, O/W. Example like mayonnaise, salad dressings, milk beverages, cream, soups, and sauce. So in some food, the dispersed phase or the continuous phase, either one of these phase, may be present in the form of partly crystalline form, rather than being completely liquid. For example, we have for example, ice cream here. So since in the ice cream we have fat, the fat come from the milk fat, or maybe other fat that we can add into the ice cream. So fat can crystallize. So depending on the temperature, at any temperature, there's always some amount of fat and some amount of liquid in the oil, in the fat. So we can measure the solid fat content actually. So that, but this fat actually can be present in the form of continuous phase, or can be present in the form of liquid phase. Sorry, as a dispersed phase, but they can be present in crystalline form. Okay. Similarly, in chocolate, the butter fat in chocolate also can crystallize. And initially, chocolate start with a liquid, in the liquid form. But when the chocolate is solidified, the butter fat in the chocolate will start to crystallize and will form like a solid phase. So the chocolate in the butterfat in the chocolate phase is in the continuous phase and can form a crystalline phase in the product. So how do we form an emulsion? So this is the last few slides that for this web lecture today. So to form an emulsion requires the dispersion of one phase to form into small droplets, and this would result in a massive increase in the interfacial area between the dispersed and the continuous phase. So we have seen just now the example that illustrate how the interfacial area increase when we disperse the droplets into a smaller size. So in order to disperse one liquid into another liquid very efficiently, we can carry out a process called homogenization by using homogenizer. So briefly, basically homogenization is the process by which the dispersed phase is broken into small droplets. By using high pressure homogenizers, the pressure can range from 10 to 100 megapascal to carry out this job. So we can see, here for example in this picture, we start with oil and water. Then we can use mechanical energy by using homogenizer or high-speed mixer, and we can disperse this liquid into this oil into the aqueous phase to form a droplet. And if we use a very high-speed homogenizer or high-speed mixer, we can get actually very fine, small droplets. Then we get an increase in the interfacial area. So for any composition of oil and water, or for any composition of emulsion, by decreasing the size of the droplet, we can increase the number of droplets, and hence we can increase the area of interfacial contact. So we can do this by using a homogenization process. In the lab, for a small amount of emulsion, we can use this type of handheld homogenizer. Then we can put the emulsion that we want to prepare in a container, in a beaker like this, and we can use this mixer, set it at the higher speed that we want to use. You can hold this by hand, or you can fix it to a stand like this, and you can form the emulsion very easily this way. So basically what happens is actually the homogenizer or the high-speed mixer will apply a very high shear force and disperse the liquid into another liquid. So the high shearing force actually will break up the liquid or the droplet into a smaller one like this. So the industrial homogenizers, there are a few types basically, but basically the principles are the same. What you need to have in this kind of instrument is to apply very high pressure. So for example, in this case we have this valve with a small gap. So when we apply the pressure, so the liquid will be forced to flow through a small gap, and therefore will be subjected to very high shear, and this will disperse the liquid into a small droplet. Same principle here and here. Okay, so the basic principle is the equipment must be able to apply very high shear. So to get a very high shear, whether you can use a very high speed like high speed mixer, or there are some way to apply very high pressure. That's the principle of homogenizer, how it works. So in this picture, for example, we have this high speed mixer, very efficient. I have linked some videos from YouTube in the Enmodo. Some of you maybe have seen this, and you can see how efficient those high-speed mixer actually form and disperse the one liquid into another to form a good emulsion. So we can install this kind of high-speed mixer into a setup like this, a tank, okay, to prepare a large volume of emulsion. So I'll say goodbye now. Thank you very much, and see you in the next web lecture. Okay.